Hey guys, we're back to talk a little more about Le Chatelier's principle, and this time we want to talk about that principle as it's related to temperature. All right, so think back to what we discussed. I believe it was last chapter. We discussed that change in G. Remember Gibbs free energy when we learned about that? Actually, I think it was last chapter when I told you this about it, but it was a chapter before we studied it. Anyway, change in G actually affects the equilibrium constant, right? So the greater the change in G, the more the equilibrium constant is affected. And so one of the things when we learned about Gibbs free energy, one of the things we learned is that it is affected by temperature. So if that's the case, and the equilibrium constant is affected by change in G, then we would assume equilibrium to also be affected by temperature. So how does that relate to Le Chatelier's principle? And it turns out that I've got a definition written down for you here that's pretty much straight from the book, but you're probably wondering, why do we have the little musical notes here? That's because I've written you a little ditty, right? I know music just has the power to convey a message and help you commit it to memory. So I want to do my part to help you commit this, the effect of temperature upon Le Chatelier's principle, which says when temp is raised, an equilibrium will shift away from the side that contains energy. When temp is lowered, it will shift towards the side that contains energy. Did I write that down right? That looks right. All right. So let's sing our little song. Okay, you ready? Me, 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 me. All right, I think we're ready. The Chatelier, he's gone away, but his principle is here to stay. Today, when the temp is raised, an equilibrium will shift away from the side that contains the energy. So I had a little hard time rhyming energy at the end there, but I think it kind of works, right? And I mean, I'm expecting this song to be a big hit, among the chemistry community. So I'll let you know how that goes. But anyway, what does this actually mean? When the temperature is raised, an equilibrium will shift away from the side that contains energy. Well, remember when we talked about energy, remember when we talked about change in H? We said that if a reaction is endothermic, change in H will be positive. If a reaction is exothermic, change in H would be negative. And we said if we know change in H, we can actually add that energy to the equation. If it's endothermic, we will add the energy to the reactant side of the equation. If it's exothermic, we would add that energy to the product side of the equation. And so what this is basically saying is that when the temperature is raised, it's going to increase the energy on whichever side of the equation that energy has been added. Okay, so if you think about that, when temp is raised, an equilibrium will shift away from the side that contains energy. All right, so because it's kind of like the concentration on that side of the chemical equation going up, right? And we said whenever concentration of something increases, then it's going to shift to the other side of the equation. And so the concentration of the energy increases as the temperature is raised. You just think about it like that. And so it's going to shift away from it. And so conversely, when the temp is lowered, it's like the concentration of the energy decreasing on that side, right? And so it's going to shift towards that side, because any time you have a decrease in concentration on one side of the equation, it's going to shift to that side. So let's do an example. Example 16.6. Example 16.6 says the following equilibrium has a change in H of negative 92.5 kilojoules. And then it gives us the equation. PCl3, which is a gas, plus Cl2, which is a gas, produces PCl5, which is also a gas. And so the question is, what happens to the concentration of the PCl5 gas as the temperature is increased? All right. So based on what we just learned concerning temperature in Le Chatelier's principle, it said that we have a change in H that's equal to negative 92.5 kilojoules. And as we said, you have a change in H here that's negative. That means it's an exothermic reaction, and it's going to be added to the product side, right? So we could just say we could add this in over here, 92.5 kilojoules. And so what's going to happen when the temperature, it says, is increased? Well, like I said, when the temperature is increased, that's as if the concentration of the energy here is going up. And anytime the concentration increases on one side of the equation, what happens? The reaction shifts in the opposite direction, right? And so what's going to happen then to PCl5, since it's going, the reaction is going to shift in this toward the reactants, then the concentration of PCl5, this concentration, right, is going to go down. It's going to decrease. All right? Okay, well, so that's enough about temperature. There's one more thing I want to talk about, and that is how Le Chatelier's principle relates to pressure. So let's consider that. You guys are going to be sad because unfortunately I did not write a song for this portion of the lecture. So let's talk about Le Chatelier's principle and pressure. All right? And the way that pressure relates to this principle, let's think for a moment, go back to, I believe it was chapter 10. I think that one was called It's a Gas. And we discussed gases extensively. And when we talked about those gases, we found out that that pressure was a big part of that discussion, right? So when we discuss gases, we need to take pressure into account, and that makes sense because gases spread out so much, and so the pressure, when it confines it, it's going to have an effect on that gas, and so it's going to have an effect, therefore, on the way that gases are related to one another in Le Chatelier's principle when we apply some pressure. And another way to think about that is remember with gases, because they do tend to spread out, whenever you apply pressure to those gases, you're going to be taking those molecules and putting them now closer to one another as the pressure is applied. And if they're put closer to one another, then you're going to increase the chance of collisions happening with those gas molecules. And if more collisions happen, then that's going to increase the reaction rate, right? There's going to be a greater reaction. And so we can also think about it that way and understand that it's going to change the way that change what's going on with the reaction, that it affects the overall reaction when it's a gas. All right. And so here's the thought with how that relates to Le Chatelier's principle. When pressure, I'm just going to abbreviate this. When P goes up, right? When P goes up, an equilibrium will shift away from the side with more gas molecules. Right? So pressure goes up, right? It's going to shift away. And whoops, I missed. An equilibrium shifts away from the side with more gas molecules. All right. So pressure goes up, shifts away from the side with more gas molecules. Let's see if it goes down. If P goes down, then we say that it will shifts towards the side with more gas molecules. All right, so pressure goes down, shifts towards side with more gas molecules. All right, and then the other thing to note is that if no gases, P doesn't affect equilibrium. All right, so you don't even have to worry about pressure changes if there aren't any gases in your chemical reaction. All right, so let's do one more quick example and we will be done with this lecture. And that example is example 16.7. on page 503. So the problem says, what happens to the concentration of the hydrogen gas in this reaction when the pressure is lowered? And it gives us this reaction C, which is a solid, plus H2O in gas form, yields carbon monoxide in gas form and H2 in gas form. And so what's going to happen to the hydrogen, this right here, when the pressure is lowered, all right? And so remember, when we talk about pressure, we just have to see which side has the most gas molecules, right? And in this case here, this has one gas molecule, only one molecule of H2O. This side has two gas molecules, one of carbon monoxide and one of hydrogen, right? So if you decrease the pressure, what we said in our statement a moment ago is that the reaction is going to shift towards the side with the most gases, right? And so that means that the concentration of H2 then, the concentration of H2 is going to increase. It will go up because it's going to shift to this side since there are more gas molecules there. Now, the second part of this particular problem involves this equation here. And it says, what happens to the concentration of the hydrogen gas in this reaction when the pressure is increased? And so the hydrogen gas is right here. So what happens to the concentration of hydrogen when the pressure is increased? And so again, pressure only matters whenever we're looking at gas molecules. And it's going to, if the pressure is increased, then it's going to shift away from the side with the most gas molecules. So let's count up our gas molecules. On this side, we got one hydrogen molecule and one iodine here. So we've got two. And on this side, we have two HI gas molecules. So we've got two on both sides. So guess what? Pressure doesn't affect it, right? We don't have one side with more gas molecules than the other. So it's going to be unaffected by pressure, and the concentration of hydrogen gas will not change, all right? So that's that problem, and that's really the last thing I want to say in this particular lecture. The other thing that's kind of cool that you might want to take a look at in your book is right at the very end of the book, there's a quote there by Dr. Schaefer, which I thought was really good. Dr. Schaefer, turns out that he is a professor at UGA. How cool is that? So in our book, we've got someone mentioned here that actually teaches here in Georgia. And he is a renowned scientist. And Dr. Henry Schaefer, it says he's director of the Center for Computational Chemistry at the University of Georgia. He has more than 1,400 scientific publications to his credit and is one of the most highly cited scientists in the world. Pretty cool. And he has this to say about science and as he studies chemistry. The significance and joy in my science comes in those occasional moments of discovering something new and saying to myself, so that's how God did it. My goal is to understand a little corner of God's plan. And so I told you guys that was my burden from the very beginning of this course, right? That chemistry was a study of what God made, right? God invented chemistry. And so really this is like everything as we observe the creation around us, we're learning about the God that made it. Ultimately, it's a study of God. That's what we need to pursue above all. And the good news is that God is a rewarder of the one that diligently seeks him. So God will always reward that with a fuller revelation of himself. All right. So that's my prayer for you guys. I pray that's what this course has been about. And I just pray that's what life will be about in general for you. That it will be about a pursuit of the one that's worthy of your full attention. About a pursuit in Jesus Christ, who deserves the glory in everything. And so may these things just give you a fuller awareness of his greatness, of his might and power. I pray you would stand in awe of him and that you would give him the glory that he's due. All right. Love you guys. See you next time.